Okay, so last time we saw one more application of Dilworth theorem on improving logarithmic Ramsey bounds for generic graphs to polynomial in N for special family of graphs. In particular, we looked at intersection graphs of geometric objects, the axis parallel, axis aligned boxes. And the idea, we saw several ideas, basically is to classify the intersection patterns of pairs by a poset relation, by several poset relations, and then we can repeatedly apply Dilworth theorem. We've also seen in these rectangle cases, the boxes, a nice application of the divide and conquer technique, which is quite a common technique in theoretical computer science and algorithmic designs. Then we mentioned about the sunflower, and we proved, so let's recall, the sunflower is a collection of sets where pairwise intersections are exactly the same for some set K, which we call kernel. And so when K is now empty, it looks like this. When K is empty, it could be just a matching pairwise disjoint sets. And Erdős and Rado, back in the 60s, proved that we don't notice that this theorem, the ground set, the size, do not play a role. The ground set could be anything. All it says is that if we have a uniform set system, a system of K sets, as long provided that we have enough sets in this system, then we can always find the sunflower with many, many petals. And the proof is by induction in K, an easy proof. So let's mention some open problems. This is lecture 16. So previously, if we define, let's define the parameter f kr to be the minimum number or the minimum size of a K uniform set system, minimum M in N, such that for any system of K sets F. So if F, the size is bigger than equal to M, then F contains a sunflower with R petals, then there F contains a sunflower with R petals. Then in this language, Erdős and Rado basically proved that FKR is less than equal to K factorial R minus 1 to the K plus 1, right? We proved that if you have more than this many edges, or at least this plus 1, you will necessarily have a petal. So this number is definitely an upper bound on this minimal M, where we guarantee to have a sunflower with R petals. Determining the growth, the order of magnitude of this function FKR is one of the major open problems in extremal combinatorics. Not just because of the by the problem itself is famous, but also this sunflower has many applications in TCS. So it spikes lots of interest in the past several decades. Recently, there's some breakthrough. So let me first mention a lower bound for FKR. So here's a lower bound. So FKR is strictly greater than R minus 1 to the K. Okay. So what does this mean, strictly greater than some number? That means we need to construct a system of K sets of this size, which do not contain a sunflower with R petals. So here's the construction. Just basically consider K uniform complete K part type hypergraph with each part of size R minus 1. So it looks like this. This is our system of sets. You have V1 dot 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 to Vk. Each Vi is of size R minus 1 for each one of them. And the edges of F are all the sets in F are all those sets that intersect each Vi at exactly 1 point. F is, I will use this symbol if you know hypergraph. If you don't know hypergraph, this is just basically all the sets such that F intercept Vi is 1 for all I in K. Okay, it looks like this. You take any K tuple. This is a hyper edge. This is a set in our system. Anyone? Then the number of sets, well, each Vi we have R minus 1 choices to pick a point. We have to do this make this decision K times. So this is the number of sets. I will leave it as exercise for you to show that this set system does not contain a sunflower with R petals. Exercise. Show that this F has no sunflower with R petals. Let's look at the lower and upper bound of this function FKR. The lower bound, let's think for a moment, R is some fixed constants. Okay. Then in terms of the uniformity, in terms of the size of the set in our member, this FKR function, lower bound is exponential in K. Some constant depends on R to the power K, exponential in K. In the upper bound, we also have some exponential in K term, similar, but the dominating term is this one. This is factorial in K, larger than exponential in K. Exponential in K is something like this, right? Factorial is more like e to the K log K. So this is much larger than exponential in K. One of the major conjecture is lower bound is closer to truth. Let me write it down. So this is Erdős-Rado's sunflower conjecture. For any number of petals, R at least 3, R is the number of petals of this sunflower, they conjecture that FKR is at most some constant C, depends only on R, to the power K. It's exponential in K at most. And this is open even for R equal to K. Just for 3 petals, we don't know. We don't have this exponential bound. So this factorial bound was recently drastically improved by a recent breakthrough. So let me mention the best known upper bound towards this conjecture. So this is recent breakthrough. By Alweiss, Lovet, Wu, and Zhang. And later improved by Rao. So the current bound is FKR. They prove FKR is at most, rather than some constant to the raised to power K, they prove something like C to the K, where C is R times log RK. Okay. So not constant. So let's forget about R. R is constant, right? Let's think of R is 3. So instead of some constant to the K, they prove this is a constant, they prove log K to the K. This is roughly E to the K log K. So in the power, we are off by a log K factor now, in terms of a K factor. This is the gap for now. Before, factorial bound of Erdős and Rado looks something like this, right? So they improve it like this. Further improving this bound will be very interesting. So if you can prove something K log K, I think it's it will be very substantial result. That's all I want to say about this. I would like to talk about this proof, but not for this beginning part. Perhaps in the fall, in the autumn, the second part of this topic course, in September, I will talk about this proof. It's a very nice semi-random method application. So let's move on to the next topic. Okay. The next thing I want to talk about is intersecting families. So let's work with how do I write it? I want to talk about a useful inequality called Harris-Gleitman inequality. But before talking about this, I would like to start with some application. So define, if we have a system of sets, F is a set system, is an intersecting family. So here the definition might be a little bit confusing. Let me first write it. It's an intersecting family if members of F are pairwise intersecting, i.e. for any F prime in F intercept F prime is not empty. So, okay. Why I say this is a little bit confusing. Before, when we talk about intersections of geometric objects, when we say a system of sets is intersecting, we usually means all the sets in this system, they have a common point. But here, in terms of Erdős-Corrado type theorem, which we will see probably next lecture, we only cared about pairwise intersection pattern. So here, it's a little bit misleading, the name, but I'm going with the convention in the literature, in extremal set theory literature. We say a family of sets is intersecting if actually it's pairwise intersecting. The members are pairwise intersecting. I'm not saying that the family of all sets in F, they have now empty intersection. This is not what I mean here. Just pairwise, they have now empty intersection. Keep in mind. So this is the definition. Now how large an intersecting family can be. Yeah, let's ask us a very simple question, some extremal question. And perhaps one of the natural extremal question is, how large can it be? How large can an intersecting family be? A very natural question. Well, here's a proposition which basically answers this question. For any family of sets, if it's intersecting, then its cardinality is at most half of all sets. So the number of all subset of n is 2 to the n, half of it is 2 to the n minus 1. Proving this is not so hard. Let's do it together. Being intersecting means for every pair, complementing pair, A bar is what? M minus A. Okay, so this is n. If you have A and you have A bar, it's complement. For these two members, you can only pick one. If both of them are presented in F, F is not intersecting, obviously. Only one could appear in F. And what is the total number of, okay? And we are done because the number of complementary pairs is what? Is 2 to the n minus 1 in all subset of n. So for all these pairs, you can only pick one. You are missing at least 2 to the n minus 1. That means F has size at most 2 to the n minus 1. This bound is obviously tight, which was already suggested in the proof. Basically, for all complementary pairs, you just pick exactly one. You can reach size 2 to the n minus 1. So here are some tight examples. The first example is you just consider all the elements, all the sets containing 1. Looks like this. This is 1. You have all those containing 1. How many such sets containing 1? Well, 1 is fixed. For all the remaining n-1 elements, you can either choose it or not choose it. 2 choices. So I have 2 to the n-1 choice. Second example is, so if you think of the 2 to the n as this Boolean lattice, the bottom is empty sets, the top is all sets. You can take all the upper half. All right. Let me see. If n is 2k, 2k, yeah. So the simplest one is probably thinking of n is odd. For now, simple case, n is odd. Let's say n is 2, let me not use k, 2t plus 1. Then you take all sets of size at least t plus 1. Okay, t plus 1 or above. Because then the 2 such members cardinality together will be 2t plus 2, which is strictly bigger than n. That means they have overlap. And the size of the upper half is half. So these are 2 typical, very natural examples. Good. Now I would like to ask the next question. Actually, before asking next question, I will leave you an exercise. I think it's a easy exercise to do. Before that, I need to define what is a maximal intersecting family definition. An intersecting family is maximal if itself is intersecting, but if you add any sets that's not in F into F, it's not intersecting anymore. If any of its superfamily is not intersecting. I.e., for any let's say A not in F, A for any A not in F, if you add A to F, it becomes not intersecting, meaning there exists a set in F which is disjoint from A, such that A and F are disjoint. That's what it means. Okay, a simple definition. It's largest in a sense. You cannot add more. Now, this exercise says we have this bound 2 to the n minus 1, which is maximum. But actually, in this non-uniform case, all maximal family are maximum size. So here's the exercise. Prove that all maximal intersecting family in 2 to the n are of size 2 to the n minus 1, maximum size. In other words, if you have an intersecting family whose size is strictly less than 2 to the n minus 1, then it's not maximal, right? So now the question, we answer the question of the size of largest intersecting family. What if we have two intersecting family, F1 and F2? They are both intersecting. Now we are asking what's the size of union of them, maximize the union of them. So here's the question. What about maximizing F1 union F2, where both F1 and F2 intersecting family? This is something we want to answer using this nice inequality by Harris and Kleitman. Okay, so let's talk about this inequality. To introduce their famous inequality, we need one more piece of definition called downsets. A family of sets, let's call it D, is a my D is horrible. How do I draw calligraphic D? So D is a downset sometimes in the literature, people also call it, this is simplicial complex. Same thing, different name, simplicial complex. All right, same name, different thing. Same thing, different name. If it's closed under taking subsets. That is, if a set T is in D and S is a subset of T, then S must also be a subset of D, a member of D. So let's draw a picture. I think the way I want to visualize it is, again, let's look at this Boolean letters. The top is the family of all sets. The bottom is empty sets. Okay, so what is a downset? If a set S is in our family, let me use a different color. S is in our family, then all its subsets. Oh, here I use T, right? Okay. So if a set T is in our family, then all its subsets are also in our family. So if you imagine T as the new ground set, all its subset itself form a Boolean lattice, a smaller copy. So here's the picture. All its subsets are also in our family. So this is in the family. Okay. Maybe I should draw a little bit smaller. Okay. So if you want to visualize it, you can pick out this D. You can look at the maximal elements in D. Should I draw? How do I draw? I think usually people think of it as like this. Okay, so if something is in there, all its subsets also in there. Something in there, all its subsets also in there. Something in there, all its subset in there. Something like this. Downward closed. Good. Now, similarly, one can define offsets. One is offsets. Oh, I used red already up there. It's offset if it's closed undertaking supersets. Meaning if T is in, let me use U for offset, shall we? So if T is in U and S is a superset of T, then S is also in U. This is offset, the opposite definition. And the offset looks something like this. You kind of flip it upside down. Okay. If a set is in there, all its supersets, think of this set now as the bottom of the lattice, or it's a superset is also in there. So the Harris-Gleitman inequality says that the following. For any downsets A and B, family of downsets, we have A intersect B, the elements, the sets that appear in both of them divided by 2 to the n is at least A cardinality divided by 2 to the n, B cardinality divided by 2 to the n. This is Harris-Gleitman inequality. So let's pause for a moment to read, decipher what this inequality is saying in the probabilistic way. If we imagine the family of all sets come with a uniform measure, uniform probabilistic measure distribution over all members, then this is exactly the measure of A intercept B. Or if you uniformly random sample an element in 2 to the n, This is the probability that X falls into A intercept B. This is the probability that X is in A. This is probably that X is in B. So if we sample uniform sample, then this Harris-Kligman inequality is saying that the probability X is in A intercept B is at least the probability that X is in A times the probability that X is in B. Let's recall basic probability. Basic probability theory says if you have two events, A and B, if they are independent, then the probability that they both happen is exactly the product of each one of them happening. So if A, B, independent events, we have equality, right? So here, Harris-Kligman is saying when both A and B are downsets, then the events A and events B, they are positively correlated, meaning that both of them happening is more likely than the product of them. This is positively correlated. If in the opposite we have this way, it's negatively correlated, right? Positively correlated. Which sort of intuitively makes sense. Why? Because when A and B are both down sets, they both favoring smaller sets. If you have another down set like this, right? They both favoring smaller sets. So it's more likely that their intersection is larger than the density of each one of them. And in the opposite, if both of them are upsets, they are both favoring larger sets. So it's also making sense that so it's also true that if you change both of them to upsets, this is true. But if one of them is upsets, one of them is downsets, they are favoring large and smaller sets respectively. So their intersection intuitively will be less than density of them product. And that's also true. If they have the opposite, they are opposites, then they are negatively correlated. So we will prove this version and leave all other versions as exercise. It's just simply modifying the proof of this version. All right. This is intuitive because being both downsets, they both favor smaller sets, right? So I will leave as exercise to prove that this variation, if A, B are both upsets, we have the same inequality. Copy. And if A is upset, where B is downset, then you have they are negatively correlated. opposite means negatively correlated. Any question about the statement? So let's prove. Let's give a proof of Harris-Gleichmann. This is proof through induction. Okay, proof through induction on the family of sets. Induction on N. Okay, let's write it. I want to introduce a notation. Okay, let me introduce this notation. If we have a family of sets, 2 to the n, and let's fix an element, I, in n, then we will write f. Do I want to use subindex, or let's use this notation, fi, which is, we have a natural way to partition f, the family f, member of sets in f. We can partition f as fi union fi bar. Let's write like this. What does it mean? Where fi is all the sets in f containing I, and fi bar is all the sets in f not containing I. There's a natural way to visualize this. So let's imagine n is 3 and I is also 3. We can associate subset members in here, subset of n with binary strings of this. You can associate it with binary strings of length n, right? Where the ith coordinate is 1 if I is in this set. Otherwise, oh, no one tell me I made a mistake here. This should be set f, right? Yeah, I made a mistake just now. So you can associate sets to 0, 1 string. So this is basically, in this language, this is all strings with 1 on the ith coordinates, whereas this is those with 0 on the ith coordinates. And if you want to draw a picture to visualize it, let's say n equals 3, I equals 3, then if your set looks like this, this is your f, then fi is here, right? This is f3, and the bottom is F3 bar. It's a natural partition where you cut the hypercube into two parallel codimension 1 subcube. And you look at the elements there, this is F3 and F3 bar. So in other words, this is partition into two codimension 1 subcubes. And look at the intersection with these two subcubes. And this is how we're going to do induction. Using this very natural partition, proof of Harris-Kleiman. Inequality. Let's rewrite this a little bit. This bigger than this is the same as, let's cancel 1 and move this to the other side. So we will use induction on n to prove 2 to the n times this is at least a times b. We will use induction on n to show 2 to the n times a intercept b is at least a times the cardinality of b. All right. Well, I think this is not quite we are using similar. Okay, so how we're going to do is we're going to partition A and B into two parts so we can reduce n. We can sort of get rid of n. How do we get rid of n? We're going to focus on the first n-1 coordinates. So partition A into which notation I want to use. Into A okay, let's partition into two parts. Those containing element n and those not containing element n. This is A. All right. And we can also define the link of n in this family A. I forgot to introduce one more notation. The link is what? It's basically, let me use symbol L of in A of n. This is basically all sets F minus n, where F is in AN. Yeah, here's a picture. So if this is element n, you look at, this is AN, right? All the sets in A containing n. Now I basically remove this element n and just focus on these sets with n removed. Remove n from all those containing n. This is the link of n. Okay. Now, the key thing is that how many sets in AN, you will get the same cardinality in LAN. The number of sets is the same. I just simply remove n from all those containing n. So easily, AN equals to link of AN. Okay. So now, what's good about it? We're going to focus on these two families now. We're going to apply induction hypothesis on those not containing n, which lives in 2 to the n minus 1 now. And this also lives in 2 to the n minus 1 and disappear in both family. Even though this is not quite its subfamily, but there's one-to-one correspondence just with n removed. So we have, let's write down the left-hand side of this inequality, 2 to the n times A union B equals to 2 to the n. So we're going to do the same partition for B, those not containing n and those containing n. So this will be the two elements appear in both A and B. If they both containing n, that will be the intersection of AN and BN, or the intersection of AN bar and BN bar. So equals to AN intercept BN plus 2 to the n AN bar intercept BN bar. This is equals to, remember we built a one-to-one correspondence between AN and the link of n, just with n removed. So this is the same if we replace the link. So this is the link of AN intersect the link of B n plus 2 to the n AN bar intercept BN bar. Good. Now we can apply induction hypothesis. Both these families, all these families, they are in 2 to the n minus 1. And they are still all in 2 to the n minus 1, and all are down sets. This is easy to check. They are still down sets. So this is at least what do I know? The induction hypothesis is 2 to the n minus 1 times this thing, at least the product of each one of them, right? Not 2 to the n. We are in 2 to the n minus 1 now. So we should have 2 times LAN times LBN plus 2 times AN bar times BN bar. Okay. So we want to compare this guy to compare this to let's call this A1, and let's call AN is A2. So we have A1 plus A2 equals to A, which is size of A, right? Similarly, define B1, B2. So we want to compare in this language, this is 2 times A1 is the link, A1, B1 plus 2 times A2, B2. What we want is bigger than, this is what we want to prove, A times B. A times B, which is A1 plus B1 A2 plus B2. Okay, let's expand right-hand side. A1, A2 plus A1, B2 plus B1, A2 plus B1, B2. So let's cancel some terms. No, we cannot cancel terms, right? I write it wrong. This is A1 plus 8. No wonder. A is A1 plus A2. B is B1 plus B2. So this is A1, B1, A1, B2, A2, B1, A2, B2. So now we can cancel one portion of this, one portion of that. So our new goal is A1, B1 plus A2, B2 minus A1, B2 minus A2, B1 is greater than or equal than 0. This is the same as we can factorize this. This is A1, B1 minus B2. A2, B2 minus B1. So it's A1 minus A2 times B1 minus B2. Let me double check. That's correct. So this is what we want to prove now. This is the new goal. Just some calculation. I did it for you. This inequality is enough to show. So I just need to show one of them is at least 0. The other one was defined similarly. So it's also at least 0. So what is this at least 0 means? Claim A1 is what? A1 is the link of n. So the link of n in A is a superfamily of the sets in n not containing sets in A not containing n. This then will imply this cardinality is A1, this is A2, so A1 is bigger than A2, and we will finish the proof. This is because A is a down set. Let's pick a set in here. Proof. Pick, let's say F in A n bar. Okay. Did I write it in a different way? It's the other way. It's the other way. Sorry. At most. So similarly, we can prove B1 is at most B2. So you have negative, negative, you get positive, all right? So let's pick not those from here, but pick the one in link of n. Good. Now, what does it mean? By definition, this means F is in the link. That means F union n is in our family A. Is in the family A. And since it's downward closed, that means all subset of it, including F itself, is also in A. But F is not containing n, so F lives in here. This implies A is downset. F is also in A. Actually, it's in A not containing n. Finish the whole proof. The proof is not long. I did the calculation once. I rarely did calculation, so I try to do once today. This is not so complicated calculation. Good. So just go back and try to read the proof, modify a little bit to prove that this exercise. Now let's see how we use them. Oh, there's a remark I want to make. This is optimal. We cannot have +1 here. Okay. Why this is optimal? Here's the example. Consider A, take disjoint set of indices A, B, subsetting N. A, B are disjoint. Now you let A, family A to be all subset of N minus B, N minus A, and B to be all subset of N minus B. Obviously, they are both downsets, close undertaking subsets. And what is A intersect B? Is all those subsets not containing elements in A, not containing elements in B. So it's all the subset of 2 to the n minus A union B. Okay, in this case, if you compute this density, it equals to 2 to the negative A plus B, which equals to size of A over 2 to the n, size of B over 2 to the n. Now let's see two applications of Harris-Kleiman inequality. The first application is the question we would like to answer here. What's the maximum size of union? Where is it? Union of two intersecting families. We're going to prove it for union of K intersect T intersecting families for fixed T. This is a theorem of Kleiman. So for any Fi, I in T, they are intersecting families, then their union I in T is at most 2 to the n minus 2 to the n minus T. Proof. This is obviously optimal, first of all. What will be T families of intersecting families, union of which realizing this size? Well, let's look. This is everything. You have to subtract something 2 to the n minus T. So let's just, you look at, you can consider Fi is all sets. Oops, what did I do? All sets containing element I. Okay. Obviously, this is intersecting, each one of which has size 2 to the n minus 1. And what's not in the union? If it does not contain any elements from 1 to t. So such set is 2 to the n minus t. We have already said this is applications of Harris-Kleiman inequality. So we have to somehow use this correlation inequality. What we do is we use induction on t, first of all. The base case t equal to 1, we've done it already by the proposition before. T equal to 1 just means you take a single intersecting family. The size is at most 2 to the n minus 2 to the n minus 1 equals 2 to the n minus 1, right? I equal to 1. This we proved it before. Now let's look at the induction hypothesis, inductive step. Suppose it's true for all I at most t minus 1. Let's prove it for t. The trick is to look at the complements of this union of Fi. Yeah. So the trick is we may assume each Fi is an offset, first of all. What does it mean each is an offset? So this is Fi, right? If a set is in Fi, we're going to take all its supersets and put it into Fi as well. This will not affect its intersecting property. And you will only increase the size of their union. It's only harming us in proving this inequality. So we may assume that. Assuming this will imply what? This will imply its complementary family, which I define to be 2 to the n minus Fi. Means whoever set's not appearing in Fi, I put it in FIC, the complementary family. It's a downset. If this is not clear, try to prove it yourself. Should be clear. Good. Now, this is a downset by induction hypothesis. Okay, let me not. Let's first write down what we need to prove. First, note that union of Fi, I in T, equals to, by De Morgan law, everything subtracting the intersection of its complementary pair. Okay, so in other words, the size of this equals to 2 to the n minus the size of intersection of this. So to get the, what do we need? We need the upper bound on this, means we need the lower bound on this. So let's give a lower bound. Let's write this as t minus 1 intercept ft. C. So think of this as one family, and this is another family. A simple property is if you have intersection of each one of them is downsets, intersection of downset is still downsets. Okay. Now it looks like the setup in Harris-Kleiman. We have intersection of two downsets. Their cardinality is at least the product of their cardinality normalized properly. Okay, so here, by Harris-Gleitman, this is at least, we should have 2 to the n. So that's product of FIC I in t minus 1 divided by 2 to the n times FTC. There should be the original inequalities are like this, right? So we cancel this factor. This is in Harris-Gleitman. Now we can use induction hypothesis on this guy. On this guy. Why? I should write it on the side. Induction hypothesis says union of Fi I in t minus 1 is at most 2 to the n minus 2 to the n minus t minus 1. This implies this is the same as, if you look at a complementary pair family, at least 2 to the n minus t minus 1. Okay? So that's first thing. Second thing, if you look at this guy, recall Ft is an intersecting family. And for intersecting family, we have this is at most 2 to the n minus 1. This implies its complementary families is at least 2 to the n minus 1. Okay. So we have this is at least 2 to the n minus t minus 1 divided by 2 to the n times 2 to the n minus 1, which equals to 2 to the n minus t, which is what we want. This is at least 2 to the n minus t, so this is at most 2 to the n minus 2 to the n minus t. Any question about the proof? It's quite a beautiful application because at the first glance, this is some statement about family of sets, different family of sets, each one of which is intersecting family. You ask for their union, give an upper bound on the cardinality of the union. It has nothing to do with probability, but we can somehow phrase it into this correlation inequality. Use Harris-Gleitman to give a short proof on that. So let's look at another application for the rest of this time of Harris-Gleitman, another nice, cute statement of Gleitman. Let me give a definition. This is sort of another complementary family, but we are not complementing by looking at the sets not in F. We are complementing elements in F. We will write F bar is the family where I take complementary sets where sets are from F. Okay, this is different from FC that we just worked with. So If this is intersecting, what does it mean? I'll leave it for you to think about it. Just draw some Venn diagram. This is intersecting means F union F prime is not the whole set for any F prime in the original family F. These two are the same statements. Okay, prove it yourself. Simple exercise. Difficulty level 0.5. Now, Kleinman's next statement is saying we gave an upper bound on the size of largest intersecting family when F is intersecting. What if we require both F is intersecting and this kind of complementary family is also intersecting? If we require both of them, what will be the upper bound? Then we can give an upper bound on the size is at most 2 to the n minus 2. Remark is how tight it is. It is tight. Consider F is all sets containing one are not containing element 2. Okay, so maybe you can write like this. If you think of it as vectors, first coordinate, we take it. Second coordinate, we don't take it. And the rest, whatever. Oops. Well, obviously, this is intersecting family. Everything contains one. And also, the complementary family is intersecting in this language. For any two sets, their union still not containing two. So not everything. How do we prove this? Harris-Gleitman's. So we have to somehow write this as a property. Write this complementary family being intersecting as another property. And look at the correlation between these two properties and use the correlation inequality. Proof. So how we're going to do it is we're going to write it like this, all right? Let's write let F upper arrow and F down arrow be the upward and downward closure of F. What does it mean? This just means for every set F in F, let me write down 1, i.e. Well, F, first of all, it's a subset of this downward closure. This consists of all the, how do I write it? For every subset of F in the family script F, we put it into downward closure. So A if A is a subset of F, okay. Good. Now let's look at each one of them. For this upward closure, how do we view it? So F is what? F are all the sets satisfying two properties, all the sets that are pairwise intersecting. This is property 1. And also, F union F prime is not everything. The complementary family is intersecting. So we can think of F as the intersection of the family that's satisfying pairwise intersecting property and the family satisfying whose complementary family is intersecting, right? This, if I call it property 1, this is property 2, then F is in property 1 intersecting property 2. Think of it like this, okay? Let's look at what actually, I don't need to write it so complicated. This is for explanation. So all we need to notice is that F is a subset of the intersection of these two sets, upward closure and downward closure, right? F is a subfamily of both of them. So to bound the cardinality of F, we just need to bound the cardinality of this guy. Now, F up intersect F down. What do I know? This guy, F itself is intersecting, taking the upward closure is still intersecting. Which is an offset. Maintaining this property. Taking downward closure, if 2 union is not the whole subset, whole set, then the downward closure, if you take 2 sets in here, still satisfying this, maintaining the second property. This is downset. By Harry-Kleiman inequality. But now we have to write at most the other direction because they are opposite monotonicity. Is at most 1 over 2 to the n times F up times F down. Okay. But what do we know about F up? F up is intersecting family. So F up is at most 2 to the n minus 1. What do we know about F down? F down is complementary family is intersecting. And this is intersecting. So it's again 2 to the n minus 1. And we finish the proof, putting these two in here. Any question? This is all I want to say about Harris-Kleiman inequality. There are extensions of this inequality, FKG, and you can find it in Alon Spencer's book, and maybe in the second half topic course, we might talk a little bit more on this. For now, that's all I want to talk about. So summarize, today we mentioned some open problems, this conjecture on sunflower, and we talk about Harris-Kleiman inequality, correlation inequality, Harris-Kleiman correlation inequality, applications on bounding union of union of intersecting families. Today, Harris-Kleiman correlation inequalities. Inequality. I think spelled it wrong. And application. All right, if there's no question, I will see you guys. Oh, there is a question.